The web device was specifically designed to address the challenges of wide-necked aneurysms. This is why the manufacturer's sizing chart focuses primarily on aneurysms that are wider than they are tall. Notice how we can visualize this relationship by drawing an imaginary diagonal line across the chart. All eligible aneurysms have a height-to-width ratio of less than 1, therefore fall below this line. For elongated aneurysms, where the height exceeds the width, the official sizing chart doesn't apply, because all of these aneurysms have a height-to-dome ratio of greater than 1, placing them above the diagonal line. Conventional methods, such as +1-1 approach, also do not work on these aneurysms, since all web devices are naturally wider than they are tall. Therefore, they will require significant lateral compression to generate the necessary height to fill the aneurysm. To choose the right web device size for elongated aneurysms, we simply swap the height and average width measurements. For example, when sizing for a 5x8 mm aneurysm, just use an 8x5 device. This will force the implant to undergo significant lateral compression to generate adequate height. Now, take a look at this unusual case. A highly elongated temporal artery aneurysm measuring 4 mm wide but 8.5 mm tall. If we flip the dimensions, we can either go for a slightly bigger 9x4 or a smaller 8x4 mm web device. So, which one should we choose? The larger 9x4 device is at risk of encroaching the origin of the temporal artery. For this reason, we'll opt for the slightly smaller 8x4 device. This approach accurately predicts the extent of vertical elongation, therefore avoiding encroachment of the origin of the temporal artery, as showed in the post-deployment run. In the same aneurysm, despite extensive lateral compression, we can still safely invert the proximal recess of the device, without risking aneurysm wall injury. This is because the radial force is spread across a wider contact area, reducing pressure on any single point. Here is another case, an acute MCA bifurcation aneurysm, where the rupture point has formed a pseudoaneurysm along the dome. Even with this irregular morphology, we can still treat it with a web device by excluding any redundant space. With measurements of 5.5 mm width and 8 mm height, our approach would be to swap the dimensions and select an 8x6 or 8x5 device. While it may be possible to deploy an 8x6 web, using the pseudoaneurysm as a buffer for potential device herniation, we went for an 8x5 mm device instead, due to the severe vasospasm in nearby vessels, which adds complexity to the deployment. While this sizing strategy works perfectly for cylindrical aneurysms, which naturally align with the web device's shape, most aneurysms we encounter aren't cylindrical. That's why it is important to modify the sizing method for non-cylindrical cases. For the same maximum width and height, a non-cylindrical aneurysm always has less volume than a cylindrical one. So if we just swap the height and width measurements, we'd actually be oversizing the device. To reduce its volume, just subtract 1 mm from the device's height. For instance, if we select an 8x5 mm web device for a cylindrical aneurysm, we should instead choose an 8x4 device for a non-cylindrical shapes of identical width and height. This 1 mm height reduction accounts for their smaller inherent volume and allows us to easily identify the correct device size, regardless of the aneurysm's configuration. Let's apply this sizing strategy to this elongated spindle-shaped ACOM aneurysm. Focus on the maximum width and height, then simply flip those two numbers and subtract 1 mm from the height. Since the aneurysm has a much smaller volume compared to a cylindrical aneurysm, with the same maximum dimensions, we decided to go for an 8x4 instead of a 9x4 web. This strategy allows the aneurysm to achieve immediate complete occlusion post-deployment, demonstrating contrast stasis with no filling beyond the neck. We also like to highlight the impact of extreme lateral compression on web device configurations. Under significant compression, The SLS model adopts a cylindrical morphology with a flattened base, while the standard SL device develops a distinct hourglass shape, effectively reversing their native base configurations. It is therefore important to be aware that under extreme lateral compression, the base of a single layered device will become more spherical in shape, which may predispose to dog ear formation in wide-necked aneurysms.